Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. In the search for carbon-free or carbon-neutral energy sources to replace fossil fuels, hydrogen is a subject of active development. In rocketry, it's a very high-performance fuel, and when reacted in moderate temperature combustion processes, the primary exhaust gas, water vapor, is harmless. But the highest quality energy in any system is electric current, and fuel cells promise to deliver direct conversion of gaseous hydrogen to electricity. Now, they've been powering spacecraft for over half a century, and there are commercial applications, but technical challenges still need to be overcome before fuel cells can become a power source for popular consumer applications like motor vehicles or home power. Now, joining me to discuss progress in hydrogen fuel cell technology is Carl Cottuli. He's head of development engineering at Bloom Energy, with responsibility for setting standards and driving global product development using fuel cell-based technology. Carl is an electrical engineer, and he has over 40 patents for power, cooling, and fuel cell devices. Carl, welcome to the Primary Loop.
Hi, thank you, Jim, for having me on.
Carl, there's so much to talk about in this technology. It's actually been around for a long time. I understand conceptually it's over a century old. It's been reliably powering sort of high-tech applications like spacecraft, since the 1960s. And it uses hydrogen, which we know is a clean fuel. So it's as if the planets are aligning for this technology at a time where we're trying to get off fossil fuel.
You're absolutely correct, Jim. One of the benefits of solid oxide technology is hydrogen is a natural fuel for the technology. It is the main component that creates the electrochemical reaction that generates the electricity. And by nature, like you had mentioned, the output product is water.
Carl, how does fuel cells work? Is this a surface chemistry thing?
Yes, it is. We actually will flow the hydrogen across a surface. We will, flow oxygen across its opposite surface. The oxygen will be forced to bond with the hydrogen, creating the energy, and the bonding actually creates the heat. And when I bond oxygen to hydrogen, and I do it twice, I get H2O. And that ends up being the output product. The benefit of it is I series and parallel these little micro reactions. I get to generate significant amounts of power that we use in a sustainable way across our technology.
Yeah. Now, in chemical engineering, of course, the catalysis people, everything is about the active sites and the surface area, and a sort of a very large surface area, of course, is what you want. And we have zeolites, and they have ways to do that. Is the same thing true in fuel cell technology with your tech? Is it a matter of getting a lot of surface area in a little box?
Yes, it is, and we do that by repeat layers. Right? We can have a standard size that makes it relatively straightforward to manufacture in mass quantities, and then we will series them up in a what we call a stack, and those will end up in columns. Columns will end up in hot boxes where that is the reaction chamber itself, and then we'll take multiple hot boxes and parallel them together for significant amounts of energy available to the end user.
Now, you mentioned, of course, heat. Heat could be thought of, I guess, as a byproduct or perhaps even a product or something usable out of this process down there. Where does the heat generation fit into the equation?
So one of the main benefits of solid oxide is it does run at high temperature. That high temperature is an end result of the electrochemical reaction, but consequently, because I have all that high temperature, I can actually have a CHP application where I'm not only producing electricity, I can produce a significant amount of heat, therefore increasing the overall efficiency of the product in a variety of different applications that need the heat as well as power.
As a process parameter, is the inlet gas temperature and pressure a factor? How do you have to condition the feed gas?
Not really. If I'm getting, hydrogen, I will condition various types of gases depending on what I'm fed. But most notably, if it's hydrogen, as you had mentioned, I don't need to really condition that. That will go in directly into the fuel cell. Everything else I do with alternate fuels, a little bit of conditioning that will happen either before the fuel cell or on the cell itself as part of a reformation process to be able to get the hydrogen atom all by itself to be able to create the bond.
How pure does hydrogen have to be for commercial applications?
Well, I mean, yeah, in the end, everybody's looking for some level of purity in hydrogen. And it really depends what the other constituents are, Jim. When you talk about impurities, Some and most are actually benign to the fuel cell, meaning they will just pass right through with the on the fuel layer with the hydrogen and pass right out. However, if they are what I'll call bad constituent, then I will have to either pre-treat that or peel that off or adjust my reaction to be able to be withstanding them. So it really depends what the bad actors are.
Sure. So is the hydrogen flow the limiting reagent? Do you flood the thing with atmospheric oxygen?
Yes. Yep. Relatively low pressure. Half a psi is normally enough.
Sure. That makes sense. So is the ambient airflow through the unit, I guess, that helps you scavenge the byproducts, the water vapor?
No, the ambient airflow is where I will scavenge the initial oxygen. To be able to create the bonding action. The rest of whatever is coming through, ambient air, mostly nitrogen, as you are probably well aware, is again passed through my device in a benign.
Sure. Now, what sort of form factor are we talking about for commercial applications here?
So on average, the size of a refrigerator would be an individual unit of ours. And that would normally produce something around the 65 kilowatts of energy. And I will parallel those together in a modular fashion to get up to multi-megawatt.
An application that came to mind immediately is I think of, say, the oil refining business, ironically, where hydrotreating is a major part of a lot of refinery operations. So they have a lot of gaseous hydrogen on hand, and they also have a need for substantial amounts of electric power. Applications like that, would that be a natural industrial use?
Yes, sir, it is. They fit well together in the petrochem environment. But keep in mind, anybody who is consuming electricity is also a natural environment. One of the better things with the fuel cell is the sustainability function. So not only do you get good clean energy, you can get the heat, and plenty of people are looking for high power, highly reliable power, and sustainability position as well. So anybody who's consuming electricity is a viable player for the SOFC technology.
Yeah. So industrially, I'm thinking then, could the heat byproduct then be used for processor space heat concurrently with electricity generation?
Oh, yes. We do a lot of process heat is coming out of the fuel cell technology. Those would be aggregated together to have a high flow rate into any type of process. You can, go make steam with it. You can heat water. You can directly into absorption chillers, make chilling. If you don't need heat and you want cooling, you can still use the heat.
Some of the pipeline people tell me that they're experimenting with entraining hydrogen gas inside natural gas flows at loadings up to 20%. Is that a potential way that you could sort of co-locate some of this generation capability and strip off some of the hydrogen in natural gas flows?
That's absolutely correct, and it is typically by mass is what we look at, because that's the important factor that we're trying to create energy with. But that 20% flow rate will be able to mix with our natural gas product and flow in a benign way into our system and be fully reacted along with the natural gas. We will treat the natural gas and break those carbon-hydrogen bonds. So those hydrogen atoms are free to bond with oxygen with the naturally flowing hydrogen that's in that stream as well.
Sure. Now, some scientists we've talked to about this technology say that the efficiencies are sufficiently high that it can actually still make economic sense to use a steam reforming process to make the hydrogen. So it still might be worthwhile to pull the hydrogen off a hydrocarbon and then feed it into a fuel cell. Does that make sense?
Exactly correct. And we actually do a piece of steam reformation on a natural gas because we have that heat that we were talking about, Jim. And we have water available. I can create the steam inside my reaction chamber and reform the fuel on the spot.
Is this a technology for multinational corporations? Are we ready for small businesses, homeowners? Where does it stand at this point of development?
Well, fortunately enough, we cover the gambit, right? We will do multi-megawatts, and, I can take you up to 100 megawatts if that's what you want, but I can take you down to a home-based system as well.
Would you typically pair that with a battery storage system for load leveling? I mean, or would you simply size up the fuel cell to accommodate peak demand?
No, it's more beneficial at that point to pair with a battery system. We do that regularly. Our system is capable of running in an island state as well, not just in parallel with other generation sources. So when we run in an island state, sometimes we'll integrate a battery, and it really depends on what the load profile is. If you've got a very steady state load profile, then a fuel cell by itself could potentially be of big benefit to you. If you have a highly cyclic load, think of an office building, Jim, where everybody comes in during the day, load peaks up, everybody goes home at night, all the lights are out, and you're very low. Perfect application for a fuel cell and battery.
Yeah. Now, it's actually a very provocative kind of installation because so much of the economy has access to piped gaseous fuels as it stands now. So a lot of the infrastructure is already in place. We're talking about the need to generate electricity in large quantities for charging potentially fleets of electric vehicles. And that might be a place where we don't have an adequate grid connection, but man, we've got piped gas. Is there a role for this in that transition of getting those charging stations on every interstate?
Yes, we that as a key growth area for the fuel cell and charger combination. It can be an easily packaged solution that you just drop, feed it, natural gas or hydrogen, and you're able to do the EV charging right then and there without any grid connection if you wanted to, or if you had a constrained grid. We do this a lot. As utility is constrained right now. Time to power is a big concern.
How far in the future do you think it will be when we reach a point where I can call in a local HVAC contractor the way I would to have a Trane or a Carrier air conditioner installed and have them drop one of these units into my basement to power my house?
I would expect that's going to be a plug and play product, particularly the home-based product, right? And even some of the standard sizes for a commercial or industrial application are already standardized that could happen. In fact, we use a whole bevy of electrical contractors, same type of electrical contractor you would call to install your new your new washer dryer or your diesel generator if you decide to do that. We use the same type of contractor technology. Yeah, dropping on the site.
Carl Cottuli, Bloom Energy, thanks for joining me on The Primary Loop.
All right, thank you.
Well, that's it for this episode of The Primary Loop, brought to you by engineering.com. For our deeper engineering series, visit engineering.com TV for exclusive shows like Manufacturing the Future, Designing the Future, and the Engineering Roundtable, not found here on our YouTube channel. The links are in the description below. Thanks for watching.